has already given to you. Okay, I will start the class shortly. Now, the attendance form, there are still a few students haven't filled up. Okay, I will wait for some of you to fill up. Okay, then after that, I will start the class. Three more students. According to the list of students here, I see in the Google Meet, and then I check in the attendance form. I see that three more students. Please fill out the attendance form. Okay, so I will start the class now. Uh, the attendance, two more students. Okay, so please fill up the form as soon as possible. Okay, today I will continue with chapter 2. That is about layout design rules. Okay, I have a stop in this topic. Okay, today I'm going to cover all, and then also together with the computer aided design tools and issue. Okay, so if I'm able to cover all these, then next I will go to the chapter 3. Okay, but chapter 3 likely I will cover on Wednesday, but I hope that today I can cover all for chapter 2.
Miss, your mic is off.
Okay, yeah, okay, thank you. Yeah, thank you for reminding. My mic is muted here. Okay, so I repeat again what I say just now. Okay, today I will continue with chapter 2. Okay, chapter 2, which is about the layout design rules. Um, okay, in the previous class, I have covered about the fabrication process and layout design rules. Okay, layout design rules is a design guideline, okay, that specify the minimum spacing and minimum width, okay, of a set of the masses. Okay, the masses here mentioned is the mass that used to form the pattern, okay, used to form the patterns of the layers on the substrate for IC fabrications. Okay, so the layout design rules here are important, okay, because they determines the measurements of the layers, okay, in IC. And the measurements here, there are two approach of measurements. Okay, just now I show you this slide. Okay, the measurements here, two approach. Okay, which are the micron rules. Okay, micron rules means that all the dimension of the layers are measured in micron meter. Okay, And another approach of measurement is in lambda rules. Okay, this lambda rules means that all the dimensions uh, of the layers, no matter in spacing or the width, the layers are measured in lambda. Okay, so I refer back to this figure. Okay, this figure shows that all the layers, the width, and the spacing are stated in lambda. Okay, you see this is lambda. Okay, lambda can be in any value. Okay, standard value. Okay, I make an assumption here. Standard value maybe lambda is 0.6 micron meter. Okay, so if all of these are stated in lambda, then we can know that this is 4 multiplied 0.6 micrometer. So this will be 2.4 micrometer. But in lambda rules, all is not mentioned in micron. Okay, it is mentioned in lambda. Okay. Okay, so you see this figure. Okay, all this figure shows the spacing and width for different type of layers. Okay, the layers here for metal one. Okay, this is a metal layer. Okay, we also can say that this is a wire. Okay, or interconnect. Okay, they are different terms, but they are of the same meaning. Okay, okay, so this is the spacing. Okay, when we draw the design, we need to make sure that a minimum spacing is followed. Okay, and then the metal, this is metal 2, is also the wire. Okay, metal 2, sometimes we also need to use metal 2 if we don't want to overlap the wire with metal 1. Okay, so we need to use another level of the layers for wire. Okay, and then diffusion. Diffusion, this is a diffusion area. Okay, diffusion area. In between there are some spacing, so the spacing must have 4 lambda. Okay, and then the width as well. And then for polygon as well, polygon, the width of the not polygon, the polysilicon, the width of the polysilicon is smaller than the width of the metal. Okay, so polysilicon, the spacing in between is different than the metal layers. Okay, so you need to be aware of this. Okay, and when you do the design, you need to make sure that the spacing between all the different layers are different, and then they follow their own their own rules. Okay, so this is a layout design of a CMOS inverter. Okay, so based on this, you will know that this is a metal. This is a metal layer. Okay, this is a polysilicon. This is a contact. Okay, so you see that these layers, the width is 4 lambda. Okay, and then here the contact here, the width of the contact here can actually refer to this one. Okay, you can refer to this or refer to this one. Okay, so the width here must be 2 lambda. Okay, so these are the design rules. Okay, that must be followed. Okay, okay, so now I go to the next slide. Okay, this slide further describe about the design rules for contact. Okay, for contact, you see that this is the figure of a contact. Okay, side view. This is a 2D side view diagram. Okay, and the top here, the black color layers is the metal. Okay, and then this is the N plus diffusions area. Okay, so here there is a contact here. Okay, this contact is to make connections with this diffusions area. Okay, this diffusions area can be source terminals or drain terminal. Okay, if we want to connect to this area or this terminal, Okay, we need to have a contact. Okay, so the contact here, there is a size. The size here must is already fixed. Okay, and must be followed. Okay, if we convert this diagram, not convert, if we view this diagram to see it from top. Okay, this is the top. Okay, we can see the contact from the top like this. Okay, and then the size of the contact is defined by D. D here. Okay, D means that the width of the width. So I draw here to show you what is D. Okay, so this is D. So the contact size is defined by D. Okay, D multiply D. Okay, and then this is a metal layer. So you see that this is a metal layer that indicate this part, okay, the black color. Okay, and then the N plus diffusions, okay, mean this one, this the dot line here indicate this area. Okay, so this contact is around here. Okay, it's not like this, but it's the lying down. Okay, it is lying down, and then from top you will see it is like this. Okay, and the statements given here for the design rules of contact, the minimum size is limited by the lithography process. Okay, so again, for the contact, the minimum size of the contact is limited by the lithography process. Okay, how do this contact is formed on the metal layers here is actually based on the use of the masses in for a lithography process. Okay, the masses must have a certain pattern or certain size to be fabricate. Okay, to form the size of the contact and fabricate it on the substrate. Okay, and then large contact can result in cracks and warts. Dimensions of contact cards are restricted to values that can be reliably manufactured. A minimum distance between the edge of the oxide card and the edge of the patterns region must be specified to allow for misalignment tolerance, or we sometimes call the misalignment tolerance as the registration errors. Okay, so you see this figure. Okay, this figure. This is the tolerance that the contact, the misalignment tolerance that is allowed for the contact. Okay, so we need to make sure that the contact is aligned. It is aligned correctly. Okay, it is aligned correctly, and then the misalignment is allowed, but with some tolerance. Okay, so you see that this um, contact, if it is misaligned to the left side or right side, okay, it is still allowed, but within the tolerance given. Okay, so this is about the minimum spacings for contact. Okay, then next is about the advantages of generalized design rules. Okay, why we need to follow the design rules, and then what is the advantages, what is the benefit that the designer can achieve. Okay, so there are a few points here. Okay, ease of learning because they are scalable, portables, and durable. Longevities of design that are simple, abstract, and minimal cluster. Increase designer efficiency. Automatic translations to final layout for fabrications. Manufacturing processes have inherent limitations in accuracy and repeatability. Design rules specify geometrics of masses that provide reasonable yield. Design rules are determined by experience. Okay, the needs for layout design rules. Okay, they are benefits. Okay, just now already mentioned some of the benefits, and then this is the reason. Okay, this is about the reason why, and then why there is a need for the layout design rules. Okay, the needs are because to achieve a better area efficiency of the IC. Okay, this area efficiency means the area of the IC. Okay, you still remember I showed you the video before. Okay, and then with uh, the wafer images. Okay, the wafer on the silicon wafer. Okay, can use to produce a chip, and then in the chip itself, there are a logic circuit. Okay, that logic circuit consists of the layers. Okay, and all the transistor in the circuit. Okay, they can be made smaller. Okay, when they make smaller, then we can actually optimize the use of the IC area. Okay, so all these we have to do the measurement. Okay, the measurement is based on the layout design rules. Okay, so the layout design rules can help to achieve better area efficiency, okay, and also better yield and better reliability, and increase the probability of fabricating a successful chip product on silicon wafer. Okay, so in a few previous slide, um, it mentions that the minimum spacing and width of some of the layers must be followed in order to avoid short and then avoid crack. Okay, so all these short and crack will cause the failure of the circuit. So if following the layout design rules, then the probability of fabricating a successful chip will be increased. Okay, so all these are the important reason why there is a need for the layout design rules. Okay, and if the layout design rules are not followed, then it will cause non-functional circuit and the design consuming larger silicon area. Okay, and the device can fail during or after simulations. Okay, so all this you have to remember and understand. Okay, there are still other more problems in manufacturing. Okay, um, even though the layout design rule is followed by the design, okay, by the designer in the design, okay, in designing the IC, okay, there are some other problems that could arise during the manufacturing. Okay, so some of these are the problems that will cause. Okay, so here are photoresist shrinking or tearing, variations in material depositions, variations in temperature, variations in oxide thickness, impurities, variations between slots, variations across the wafer, variations in threshold voltage. Okay, the variations of threshold voltage can be caused by the oxide thickness, okay, ion implantations, poly variations. Okay, and then diffusions, change in doping. Okay, so diffusions here, if we want to form a diffusions area, then the dopant that is used, maybe there are some changes, okay, in its characteristic, okay, in its properties. Okay, so the changes here in doping will cause variations in the resistance or capacitance. Okay, and polymetals variations in height and width, shorts and opens, wire may not be cut all the way through, or undersized wire has too much resistance, or oversized wire may be short. Okay, so all these are the problem. Okay, some maybe it's a technical problem, okay, that could face during the manufacturing. Okay, so as a summary, layout design is a schematics of IC which describe the exact placements of the components for fabrications. Layout design rules describe how small features can be and how closely they can be packed in a manufacturing process. In digital system, the transistors are chosen to have minimum possible length because short channels transistors are faster, smaller, and consume less power. Industrial design rules are generally specified in microns. This makes migrating from one process to more advanced process difficult. Okay, this is difficult, not difficulty. Okay, so because not all the rules scale in the same way. Okay, so to bring the uniformity, okay, the lambda space design rules are popularized, okay, based on a single parameter. Okay, so this is the summaries for the layout design rules. Okay, so now I will go to the next one, the next topic under chapter 2, which is the computer-aided design tools. Okay, computer-aided design tools and related issue. Okay, so this is about the tools that is used to edit and create the design. The design can be in schematic design or in layout design. Okay, so for this topic, um, the functions of the CAD tools for the layout design will be mentioned, and then some other issue that some of the issue that cover also will be mentioned, okay, that include the issue on the design. Okay, what is the issues that we will see from the layout design, okay, and then how the tools can help to solve the issue. Okay, overview of the CAD tools. The complexities of the IC is increasing over the years. Circuit design implementations progressively complex and has become has become progressively complex in deep submicrons technology. Multiple processor cores, input-output, several types of memory, complex analog circuits, and synthesized logics are being designed onto the same chip. Designing of VLSI circuit with millions of transistors in single IC require the computer-aided tools. To design VLSI circuit, computer is required to check layout, circuit performance, process, and etc. It can aid in the design and optimizations process. VLSI designers are normally given a set of design rules based on given technology. VLSI CAD tools have the following tools or functions to meet the design features. Okay, the first one is the physical design. Okay, one of the functions here is the CAD tools has the functions for the designer to design. Okay, the physical designs here as given, the layout, editor, and circuit schematics. Okay, it means that in the tools, designers are allowed to create a layout or circuit schematic, and then there is an editor functions, okay, for the designer to do that. Okay, and then after the design can be verified. Okay, we call it as physical verifications. Okay, so the verifications here refers to the DRC, the design rules checking. Okay, and then others here is given it as a circuit extractor, plot output, and visual checking. Okay, this one also include another verifications. Okay, not just DRC, there is also ERC. Okay, ERC and others verifications process. Okay, depending on what is the designs that you want to verify. Okay, um, before you stimulate the designs to obtain and to observe the operations of the design circuit, okay, we have to verify it first using the DRC, okay, and ERC, okay, if you want to make sure that the circuit can function well. Okay, and then not only that, the CAD tools can also perform behavioral verifications. Okay, these behavioral verifications means that the design can actually um, can be verified. Okay, its behavior in the tools. Okay, some of the tools here can actually convert the layout designs uh, to the layout design, okay, to programming form. Okay, the programming form, what I mean here is the VHDL code. It is in code form. Okay, after we design logic gates, okay, in schematic or layout, some of the VLSI CAD tools can actually convert it to VHDL codes, okay, to describe its behavior. Okay, and then we can actually verify the behavior of the circuit, okay, in the tools, using the tools. Okay, why there is a need of the CAD tools? Okay, here the slides, okay, stated about that. Okay, it is to ensure the product reliability to achieve a good yield. Okay, this is a significant concern. And then the electronics design automations. Okay, EDA Industrial has provided physical verifications tools to cover the growing requirements for physical implementations of circuit design. Design rules checking DRC and layout versus schematic LVS verifications processes have been evolving tremendously to be able to verify the increasing complexities of design rules and advanced device parameter extractions. Okay, this is the importance of the CAD tools. Okay, just now I want to mention, but I forgot to mention. Okay, the CAD tools here uh, is the electric. Okay, you can refer it to the electric. Electric is one of the VLSI CAD tools. Okay, another one is Cadence. Okay, this is used by the designer in industrial. Okay, the designer in industrial, they use this software. Okay, this software is an expensive software, and then they uh, need to buy. Okay, and they need to buy, and we need to get the license to use it. Okay, and then there is another software which is the Psygnosis. Okay, how to this is NOP. Okay, this is another software. Okay, this software is also expensive. We need to buy the license to use it. Okay, but normally in university, we don't buy this tool. Okay, um, if the university have the money, then of course they can buy this software, the Synopsys. Okay, but if we want to reduce the cost, we can actually use the electric. Okay, VLSI software. This is a freeware. Okay, so this is the one that you use. Okay, so all these can use to perform the physical design and verifications. Okay, for a design rule check, uh, it is about the physical checks of metals width, pitch, and spacing requirement for the different layer, which depends on different technology nodes. Layout of a design must be in accordance with a set of predefined technology rules given by the foundry for manufacturability. After completion of the layout and its physical connections, an automatic program will check every polygon in the design against these design rules and report any violations. There are a few design rules at different technology nodes. Okay, so here the points given in these slides um, are the how should I say it? Okay, okay, design rules check is a DRC. Okay, what does it check is all these are the spacing width and the area that the DRC will check. Okay, so you see that minimum width and spacing for metal, minimum width and spacing for wire, fat wire keep out enclosure, end of line spacing, minimum area, over max stack level, white metal joint, misaligned wire, okay, different net spacing, spatial notch spacing, short violations, different net wire cut spacing, less than minimum edge length. All these are checked by DRC. Okay, after the design has completed. Okay, and then there are a few of the cases here. Case A to case C. Okay, this case A to case C are shown in the next few slides. Okay, in slide 9 and 11. Okay, these are the practical problems and the solutions for different types of DRC and their solutions. Okay, so the first one, okay, this is the case A. Case A where there is a short violations. Okay, the problems here means that there is a violations. What is meant by the short violations here is two or more different nets segments of the same layers were crossing each other. Okay, so you see the diagram here. Okay, this is the layer. Okay, and this is the layer. You see the layers with the black color. Okay, so this at this point they are crossing between two layers here. Okay, we call this as a short violations. If there is a overlapping or there is a closing here, when we perform the DRC, there will be an error. Okay, there will be an error. Okay, this is one of the issues that arise when we perform the DRC with this design. Okay, and we can solve this by removing or we reposition. Okay, uh, the layers. Okay, to make them not to overlap. Okay, so this is another design without the closing. Okay, okay, how do we identify it? Okay, that this two design is the same one. Okay, you see that this layer, okay, is actually this layer. Okay, and then this one is this one. Okay, this one is okay, this one okay. Okay, now the problem is here, this one. Okay, to make this not to overlap with this layer. Okay, so this one is actually extend longer. Okay, extend longer to make these layers not to overlap with this. So this will be here. Okay, you see that this, sorry. Okay, you see that this layer is actually overlap with this, but remember they are of the different level of layers. Okay, so they are actually not overlapping. Okay, so to solve this problem, we can do it this way. Okay, this is the design that will solve the error. Okay, so here there is a statement. To fix these short violations, different net segments on same layers has to be placed away so that they will not cross each other. In this case, net adjusted net will not cross each other and also meet the spacing requirement in the same layer. Okay, so this one is without crossing. So this one is one of the issue. Another one is case B. Okay, this is about minimum area requirement. Minimum area requirement for every segment in a layout. Okay, so some of the area here. Okay, the area here, what I mean is determined by the width and the length. Okay, in the software tools that we use, the width and length of the layers are fixed. Okay, but sometimes the width can change. Okay, we can change it manually. Okay, we also need to observe that some of the width of the layers, after we change it manually, is it acceptable or not? Okay, but for this case, according to this design, okay, it looks like this area of the layers is thinner. Okay, is thinner, and then it has issue. Okay, after perform with the DRC. Okay, and then to fix it, okay, this is the area of the layers. Okay, this is with no issue. Okay, so given in the statements here, the area of the segments that will not violate the others design rules will need to increase. Okay, so this area of the layers has already increased if you compare to this one. Okay. Okay, so I go to the next one. This is another issue. Okay, this is about the misalignment of the wire. Okay, and okay, you see that this type violations pops up when two different layers of same logical net connected by inserting the wire. If inserted wire is not aligning with the metal crossings, we are seeing the wire misalignment. Okay, so you see that there are two layers here. This is the layers. Okay, and then this layer, the crossing here must be connected with a contact. Okay, okay, wire here, but okay, sometimes I call it wire. Okay, and okay, this wire is also means by the contact. Okay, okay, this is contact. So the contact here means this part. Okay, so you see that this contact is a slightly misaligned. Okay, we can actually realign it. Okay, to make it align properly with the crossing between the two layers. Okay, so after aligning it properly, okay, it will look like this. Okay, this one look like this part. This is the part that show this one. Okay, so this is the solutions. Okay, so the issue shown here just these three issue. Okay, from the three examples here. Okay, so now I will get goes to the electric rules checking ERC. Okay, for this topic, the subtopics here about the CAD tools, mostly it is about theory. Okay, the theory on the DRC, ERC, and what else? And NCC. Okay, but NCC I will not mention here. Okay, I will only mention on the DRC and ERC and also This one, okay, so the one that is in this slide ERC, what is it about? Okay, okay, so we see the statements given in the slides here. Complex circuit issues such as latch-up, noise immunity, floating spins, cross-power domains verifications, and linkage currents require verifications technique that can combine physicals and electricals informations to understand more complex connectivity and greater design context. Without ERC checks, designer cannot adequately verify the robustness of a schematic or layout design to ensure that circuit will operate as designed and the circuitry is well protected against potential electrical functions. Not complying with these rules can result in reduced yield, defect escape to customers, and delay failure in the field. Tra- Traditional ERC involves circuit simulations or fault analysis, typically verifies elemental electrical design rules, using basic connectivities and device information to find issues. Such issues include checking floating devices, floating nets, floating pins, connecting high voltage to thin gates, and maximums allowed series pass gate, and etc. Such ERC executions has usually been enabled with design rules checking and layout versus schematics verification tools. Advanced ERC has become an important part of design verifications for any integrated circuit chip design. Advanced ERC tools can provide automatic sign-off quality circuit verifications for electrostatic discharge. In short, we can call it as ESD, and electrostatic overstress EOS, multiple power domains, and advanced ERC. Okay, so from the point given here, we can know that ERC is actually check the electricals related characteristic in the circuit. Okay, uh, okay. So what is ESD? Okay, ESD is stands for the electrostatic discharge. Typically, ESD causes more than one-third of the field failure in the semiconductor industry. ESD-induced failures in semiconductor can be seen in the forms of linkage, short, burns out, contact damage, gate oxide ruptures, and resistor metals interface damage. CMOS scaling reduces power and increases speed, but smaller size increases susceptibility to damage of the thin gate oxide due to EOS or ESD conditions. Okay, the shrinking size of semiconductor chips, thin gate oxide, multiple power supplies, chip complexity, and high-speed circuit operations all contribute significantly to ESD sensitivity. Shrinking gate oxide thickness need less voltage to be damaged. It is tedious to predict ESD because ESD phenomena happen on both a microscopy and macroscopy physical layer. ESD protections design is a major challenge for IC designers. Okay, next is about ESO. Okay, about this ESO and ESD. Okay, I just cover the fundamental knowledge about these two. Okay, ESO and ESD. Okay, but in your lab, okay, you also need to perform in the software, the electric software, you need to perform the ERC. Okay, but the ERC that it's performed, it didn't check these two, um, this ESO and ESD. Okay, it only check the wheel. Okay, this one, okay, you just try to understand. Okay, and then this is just for your knowledge. Okay, what is actually to be checked in ESD. Okay, so now I will go to this ESO, electricals overstress. Okay, what is meant by ESO? Okay, so electricals overstress describe the thermal damage that may occur when an IC is subjected to a current or voltage that is beyond the datasheet specifications limit of the device. And ESO, this is ESO, okay, wrong spelling. Okay, so the correction needs to make here. This is ESO. Okay, an ESO event can degrade the IC or cause permanent functional failure. ESO is a much slower phenomenon than ESD, but the associated energy is very high. The high current in an ESO event can generate localized high temperature in the low resistance path. Okay, the high temperatures damages device material such as the gate oxide and interconnects causing metal burns out. Okay, okay. So you see that ESO is about electricals overstress. Okay, we could actually relate it uh, to the wire. Okay, the size of the wire, okay, can actually affect the amounts of current that it can flow through. Okay, uh, so if the current is high, then we need to make sure that the wire, okay, in the layout design, the wire, we call it layers. It is defined as a layers. Okay, so the size of the layers must be at a uh, must be with the requirement, okay, that can sustain high current. Okay, if not, the layers will spoil easily, okay, due to overcurrent. Okay, so this one we have to consider when we design the uh, circuit using layers. Then we have to consider the size. Okay, the size is in width and length for the area. Okay, and then to uh, we consider this because we want to make sure that there is no electrical failure. Okay, and then in the industrial they will perform this ERC. Okay, this ERC include the checking for this one. Okay, ESO. Okay, so this is the next slide that shows the electrical rules checking in electric software. Okay, so you are familiar with this. Okay, this is I copy from the electric software. Okay, is in this electric rules checking ERC. Okay, there is a check wheels and antenna check. Okay, so this one the uh, functions of the wheel checkers is to make sure that there are wheels contact in every areas of in every areas of well. The well checkers also checks that there is a connections to power and ground in the appropriate places. An additional well check is to find the furthest distance from a substrate contact to the edge of that area. This check takes more times to do. Okay, in electric, the Welsh checkers can check spacing rules between valve areas. Although this is generally the domains of the design rules checkers, it can be requested here by checking check DRC spacing rules for valve. Okay, since the valve checkers has not been designed for for DRC purposes, the algorithm is not efficient and therefore the option is off by default. Okay, so you see here, Okay, this is the setting for the well check. Okay, if you want to change the setting, you can go to the preference. Okay, under file. Okay, then there is a well check here. So when you click here, you can actually change the setting here to check the Diracy spacing rules for wheels. Okay, but check by checking here. Okay, but if you don't want, then you need to uncheck. So all these are the functions that the wheel checker will check, okay, in the layout design. Okay, so as a summary, for design rules checks, it is to check the minimum line width, spacing for metals and wire based on the design rules. Okay, ERC, electrical rule check, is to check the short circuit between power and ground, or check the floating nodes or devices. Okay, so this power and ground, they are connected through the contact. Okay, so this ERC will check the contacts in the wells. Okay, and then the layout versus schematic, this is LVS, is to verify the consistency between schematic and layout, and to check the amounts of transistor numbers, size of width over length. Okay, so for this one, okay, this LVS, LVS is to check the consistency between the schematic and layout. This is quite similar to the NCC. Okay, NCC is the network check consistency. Okay, so whenever you have done a layout design, you need to perform this NCC. Okay, if there is any difference between the schematic and layout, NCC will show the error to you. Okay, and then you need to identify where is the error that give you. Okay, uh, you have to check, what is the error between the schematic and layout design. Okay, usually when we want to draw the logic circuit, we need to draw it in schematic and layout. Okay, so the circuit must be of the same design, okay, but in different representations. Okay, if NCC give an error or give some errors, that it means that your design in schematic and layout for that circuit is not the same. Okay, it is not the same. Maybe the port, the numbers of port is different, or the names of the port is different. Okay, they must be consistent. Okay, so this is the end of the topic for the computer aided design tools and its issue. So I will stop here today. Okay, so I see that now is already 11:30. We still have another class, tutorial class for group 2. Okay, before we dismiss, let me check again the attendance form. Okay, looks like all of you have already filled up the form, except one student. Okay, one student is absent today. Okay, so attendance form, no issue. So I will continue the new topic, no new topic, the new chapters, okay, on Wednesday. Okay, so I will see you again on Wednesday. And students from group 2, you need to stay back. Okay, we still have 1 hour tutorial. And about practicals, okay, I just remember about the practicals today. Okay, there will be practical class this afternoon for group 1. Okay, for group 1, so this will be your lab 2. Okay, and then tomorrow, there is one practical class. Okay, the practical class is for group 2. Okay, group 2, you will be having the first lab tomorrow. Okay, so I want to fix it this way. On Monday, practical class is for group 1. Okay, and then not tomorrow, it's Wednesday. Okay, so I just now I mentioned wrongly. Okay, so on Wednesday, Wednesday practical class, I want to fix it for group 2. Okay, so for start from week 3 until week 3, 4, 5, 6 until week 6. Okay, the practical class will be like this. Okay, Monday for group 1 and Wednesday for group 2. Okay, so any questions? If no questions, then we can dismiss class. Okay, okay, thank you to all.